Have you ever noticed that toast always seems to land butter side down? It's one of those everyday frustrations that feels like the universe is conspiring against us. But what if I told you that this mundane kitchen disaster actually connects to some of the most fundamental laws of physics, from gravity and rotational dynamics to quantum mechanics and chaos theory? Picture this. It's 6:42 a.m. on a Monday. You're running late. The toast pops up from the toaster, perfectly browned. As you reach for it, it slips from your fingers. Time slows. The toast rotates in mid-air, almost gracefully. You watch, helpless, as the laws of physics unfold before your eyes, knowing with certainty which side will hit the floor. Butter down. Always butter down. But why? This is not just bad luck. It's physics at work. And understanding why toast falls the way it does might just help us understand how the universe operates on scales both massive and minute. Our story begins not in a kitchen, but at a prestigious physics conference in 1995. Dr. Zachary Landsman, a young physicist with a reputation for tackling unusual problems, was presenting his work on angular momentum in everyday objects. During the coffee break, a colleague jokingly mentioned the toast problem. Why does toast always seem to land butter side down? The room erupted in laughter, but Landsman didn't join in. Instead, he grabbed a napkin and began scribbling equations. What started as a joke quickly morphed into a genuine scientific inquiry. Could physics explain this seemingly trivial phenomenon? Most people would dismiss this as confirmation bias. Landsman later wrote in his journal, "We remember the messy outcomes and forget the times toast lands butter side up. But my intuition told me there was something more fundamental at play." Landsman wasn't the first to ponder this question. In 1991, British physicist Robert Matthews had published a paper in the European Journal of Physics titled Tumbling Toast, Murphy's Law and the Fundamental Constants. Matthews suggested that the phenomenon wasn't random but governed by physical laws related to how objects rotate during falls from typical table heights. The history of this inquiry goes back even further. In 1884, James Payn wrote in the Illustrated London News about the perversity of inanimate objects, noting how bread and jam invariably lands face down. This observation predated what would eventually become known as Murphy's Law. If anything can go wrong, it will. Named after aerospace engineer Edward Murphy in 1949, this principle emerged during safety tests for high-acceleration rocket sleds. When a technician incorrectly installed strain gauges, Murphy reportedly remarked, "If there's any way they can do it wrong, they will." This pessimistic outlook somehow resonated with human experience and entered popular culture. But could this law actually have a basis in physics rather than just pessimism? Felicity Kline, a professor of fluid dynamics at MIT who would later collaborate with Landsman, approached the problem from another angle. "People think scientists only care about grand cosmic questions," she said in a 2005 interview. "But understanding the ordinary can lead to extraordinary insights." The falling toast problem sits at the intersection of gravity, aerodynamics, rotational dynamics, and even chaos theory. The more scientists examined this seemingly trivial problem, the more complex it became. Initial experiments suggested that the height of a standard table, around 30 inches, and the typical dimensions of a slice of toast created the perfect conditions for a half rotation during a fall, precisely enough to turn a piece of toast from butter side up to butter side down. But this was just the beginning. As researchers dug deeper, new questions emerged. Does the weight distribution of the butter matter? What about air resistance? Does the initial position on the edge of the table influence the rotation? And perhaps most intriguingly, is this phenomenon an example of a deeper principle about how order and disorder function in our universe? These questions would lead scientists down a rabbit hole of inquiry, connecting this kitchen calamity to principles that govern everything from planetary motion to quantum fields. The humble falling toast was about to reveal insights that extended far beyond the breakfast table. As Landsman prepared to conduct his first formal experiments in 1996, he posed a question that would guide the next decade of research. What if the butter side down phenomenon isn't just an annoying coincidence but a perfect example of how complex systems behave in our universe? Landsman's initial experiments seemed straightforward. He built a simple apparatus, a platform that could push toast off a table edge with precisely controlled force. High-speed cameras recorded each fall, tracking the rotation angle as the toast descended. The results were surprising. Out of 100 trials with unbuttered toast, 62 landed butter side down. This was statistically significant, well beyond random chance. When actual buttered toast was used, the number climbed to 81 out of 100. Something fundamental is happening here, Landsman noted in his lab journal. This isn't just about bad luck. To eliminate variables, the team standardized everything. The toast was cut to identical dimensions, toasted to the same degree, and buttered with precisely measured amounts of butter distributed evenly. They even controlled for air currents in the laboratory. The mystery deepened when Felicity Kline joined the project in 1997. With expertise in fluid dynamics, she suggested that air resistance might be playing a crucial role. Air is not nothing, Kline explained. It's a fluid that interacts with falling objects in complex ways. The butter creates a slightly different surface texture and weight distribution that could affect how air flows around the toast as it falls. To test this theory, they repeated the experiments in a vacuum chamber. The results shifted dramatically. Without air resistance, the toast landed butter side down only 52% of the time, essentially random chance. Air resistance isn't just a minor factor, Kline concluded. It's fundamental to the phenomenon. But this raised a new question. Why would air resistance preferentially cause the toast to land butter side down? The team developed a mathematical model incorporating the physics of falling objects. When an object falls from a table, it doesn't just drop straight down. Pivots around the edge, gaining angular momentum. This rotation continues during the fall, and the number of rotations depends on several factors. Height of the fall, size of the object, distribution of mass, and air resistance. For typical toast falling from a standard table height, 30 inches, there's just enough time for about half a rotation. If the toast starts butter side up on the table, half a rotation puts it butter side down on the floor. It's like a cosmic conspiracy, Landsman remarked during a lecture in 1998. The height of our tables, the size of bread slices, and the properties of Earth's gravity combine to create this perfect storm of culinary disaster. But the team wasn't satisfied. Why had the buttered toast in their experiments landed butter side down more frequently than unbuttered toast, even when controlling for all other variables? This led to a series of more sophisticated experiments exploring how the physical properties of butter affect the toast's interaction with air. They discovered that butter changes not just the weight distribution but also the aerodynamic properties of the toast surface. In 2000, they published their findings in the Journal of Fluid Mechanics, demonstrating that the slightly uneven texture of buttered toast creates microturbulence patterns in the air flowing around it during a fall. These turbulent patterns exert tiny forces that, when accumulated, tend to stabilize certain rotational trajectories over others. Meanwhile, Robert Matthews continued his own research, approaching the problem from a different angle. He proposed that the initial conditions of how toast slides off a plate or table edge significantly influence its fall. His paper, published in 2001, suggested that friction between the toast and table surface causes a slight initial angular velocity that predisposes the toast to complete approximately half a rotation during a typical fall. The plot thickened when Dr. Howard Jenkins at the University of California published contradictory findings in 2002. His experiments showed no statistical preference for butter side down landings. The scientific community was puzzled by the discrepancy until it was discovered that Jenkins had conducted his experiments using square tables with rounded edges, while Landsman and Kline had used rectangular tables with sharp edges. The initial conditions matter enormously, Landsman explained. The shape of the table edge, the way the toast slides off, even microscopic variations in the surface. All these factors feed into a complex system where small changes can lead to dramatically different outcomes. This sensitivity to initial conditions pointed to something profound. The falling toast problem exhibited properties of chaos theory. Chaos theory, popularized by mathematician Edward Lorenz in the 1960s, deals with dynamic systems highly sensitive to initial conditions. Small differences in starting conditions can yield widely diverging outcomes, making long-term prediction impossible despite the underlying deterministic nature of the system. This is famously illustrated by the butterfly effect, The notion that a butterfly flapping its wings in Brazil might influence a tornado in Texas. What we're seeing with toast is chaos in action, Kline said during a 2003 lecture. The complex interaction of gravity, air resistance, angular momentum, and the initial conditions creates a system where outcomes are deterministic but practically unpredictable without incredibly precise measurements. To demonstrate this principle, the team designed an experiment where they varied the initial position of the toast on the table edge by just 1 millimeter increments. The results were striking. Minute changes in starting position led to completely different landing orientations. By 2004, what had started as a quirky investigation had evolved into a serious scientific exploration of chaos in everyday systems. The research attracted funding from the National Science Foundation, which recognized its potential to illuminate how chaotic systems behave in controllable laboratory settings. The team expanded their investigation to explore whether the butter-side-down phenomenon was merely a special case of a broader principle in physics. They began testing other flat objects with asymmetric weight distributions, playing cards with a dab of clay, thin wooden discs with metal inserts, and even custom-manufactured test objects with precisely controlled mass distributions. A pattern emerged across all these experiments. For objects falling from table height, asymmetric weight distribution consistently increased the probability of landing with the heavier side down, but only when air resistance was a factor. In 2005, Landsman proposed what he called the principle of asymmetric chaos in falling objects. In systems where rotation is influenced by both gravity and fluid resistance, objects with asymmetric mass or aerodynamic properties will tend toward orientations that maximize resistance during fall. This wasn't just about toast anymore. It potentially explained phenomena ranging from how leaves fall from trees to how certain seeds disperse in wind. Yet another layer of complexity was added when the team began considering quantum effects. At the microscopic level, the butter creates an uneven surface with varying electromagnetic properties. Could these microscopic differences, amplified through chaotic dynamics, be influencing the macroscopic outcome? Dr. Richard Feynman had once famously said, "There's plenty of room at the bottom," referring to the vast potential of manipulating matter at atomic scales. Perhaps there was also plenty of explanation at the bottom, microscopic interactions scaling up to create the familiar frustration of butter-side-down toast. To investigate, the team collaborated with material scientists to analyze the surface properties of buttered toast at microscopic scales. Using electron microscopy, they observed how butter created an irregular landscape of fat globules and moisture that changed the surface tension and electromagnetic properties of the bread. "We're seeing a bridge between quantum physics and everyday experience," Landsman noted in a 2006 paper. The microscopic structure of butter on toast creates subtle electromagnetic interactions with air molecules that, when amplified through chaotic dynamics, influence the macroscopic rotation. This connection between quantum physics and everyday objects excited the scientific community. It suggested that quantum effects might be more relevant to macroscopic experiences than previously thought, blurring the traditionally strict division between quantum and classical physics. By 2007, what had begun as a lighthearted investigation had spawned 3 doctoral dissertations, 17 peer-reviewed papers, and a book contract. The humble falling toast had become a vehicle for exploring fundamental questions about how complex systems behave. But the most startling discovery was yet to come. In preparing for a comprehensive review of all their data, Kline noticed something odd. The probability of butter-side-down landings had a slight but measurable correlation with atmospheric pressure and humidity. "We thought we'd controlled for everything," she said. "But it turns out the weather itself might be influencing our results. The plot literally thickens when the air does." This observation led to a new series of experiments conducted in controlled environmental chambers where temperature, pressure, and humidity could be precisely regulated. The results confirmed Kline's suspicion. Atmospheric conditions subtly affected the probabilities. On humid days, the butter-side-down probability increased by approximately 4%. The team hypothesized that water molecules in the air changed the nature of the air resistance acting on the toast, particularly how it interacted with the fatty butter surface. The implications were profound. If something as simple as toast falling could be influenced by such a complex web of factors, from table height and bread dimensions to atmospheric conditions and quantum effects, What did this say about our ability to predict outcomes in other complex systems? We've stumbled onto something much bigger than breakfast disasters, Landsman remarked in a 2008 interview. We're seeing how chaotic systems operate in the real world, where multiple forces interact across different scales to produce outcomes that are deterministic yet practically unpredictable. The humble falling toast was revealing a universe far more interconnected and complex than anyone had imagined. In 2009, everything changed. Landsman and Kline were preparing for a routine demonstration for a science documentary when something unexpected happened. They had set up their standard apparatus, but the film crew asked for multiple takes of the same drop to capture it from different angles. After the 12th consecutive drop using the same piece of toast, which by then was quite stale, they noticed something odd. The toast was no longer landing butter side down consistently. In fact, it seemed to be following a pattern: 3 landings butter side down, followed by 2 butter side up, then repeating. At first, we thought it was equipment failure, Landsman recalled. But when we analyzed the high-speed footage frame by frame, we saw something remarkable. The toast was deforming slightly during each impact. The repeated falls were gradually changing the toast's physical structure, altering its rigidity, center of mass, and aerodynamic properties. The toast wasn't the same object anymore. It had a memory of its previous falls encoded in its physical structure. This observation led to what would become known as the Landsman-Kline memory effect in materials physics. They had discovered that even seemingly simple objects like toast can exhibit complex material memory, where past events leave physical imprints that influence future behavior. We weren't just studying a falling object anymore, Kline explained. We were observing how matter itself encodes information through structural changes. This discovery connected the toast problem to emerging research in material science about mechanical memory in physical systems. Similar effects had been observed in complex materials like certain alloys and polymers, but never in something as ordinary as a piece of toast. The team expanded their research to explore this memory effect systematically. They designed experiments where toast was dropped repeatedly under identical conditions, documenting how its falling behavior changed over time. They found that the toast would eventually settle into predictable patterns of rotation that differed from its initial behavior. This led to a breakthrough realization. The falling toast problem wasn't just about a single drop, it was about the history of the system. The true physics of falling toast couldn't be understood by isolating a single event but required considering the evolutionary trajectory of the toast through time. It's like trying to understand why a river flows in a particular direction, Landsman explained in a 2010 lecture. You can't just look at the water molecules and the current gravitational forces. You need to understand how the riverbed was formed over centuries, how previous water flow carved channels that guide current flow. This insight transformed their understanding of the original question. The reason toast tends to land butter side down wasn't simply about table heights, rotation rates, or even air resistance in isolation. It was about how these factors interacted with the physical history of the toast itself, from how the bread was baked, creating an inherent structural asymmetry, to how it was buttered, changing its mass distribution, to how it was placed on the table, establishing initial conditions. In 2011, they published their comprehensive theory in the journal Nature Physics. The paper, titled Temporal Evolution and Memory Effects in the Dynamics of Falling Toast, presented a unified framework that incorporated all their discoveries. 1. The geometry of human furniture, table height, combined with typical toast dimensions creates conditions for approximately half a rotation during a fall. 2. Asymmetric mass distribution due to buttering predisposes the toast toward certain rotational patterns through interaction with air resistance. 3. Microscopic surface properties of butter create complex interactions with air molecules that influence rotational dynamics. 4. The initial conditions of how toast slides off a table edge introduce chaotic elements that make precise prediction difficult. 5. The physical structure of the toast itself carries a memory of its history that influences its behavior during a fall. The paper concluded with a statement that would become famous in physics education. The falling toast problem demonstrates that even in seemingly simple systems, we observe the convergence of multiple physical principles across different scales, from quantum interactions to classical mechanics, unified through the mathematics of chaos and complex systems. The scientific community was captivated. The work was featured on the cover of Scientific American. Popular science publications declared it the most comprehensive explanation of an everyday phenomenon ever developed. Universities began using the falling toast problem as a teaching tool for introducing students to concepts ranging from Newtonian mechanics to chaos theory. But perhaps the most profound impact came from the sixth and final experimental series Landsman and Kline conducted in 2012. They investigated whether human intervention could override the butter-side-down tendency. They designed a simple device, essentially a specialized plate with a small lip, that altered how toast slides off the edge when pushed. This changed the initial conditions enough to reverse the typical outcome, resulting in toast landing butter side up approximately 80% of the time. This might seem trivial, Landsman said, but it demonstrates something profound about our relationship with physical law. The universe isn't conspiring against us. Once we understand the principles at work, we can work with them rather than being victims of them. This insight extended far beyond toast. It suggested a new way of thinking about complex systems, from climate patterns to financial markets. Rather than seeing chaotic systems as fundamentally unpredictable, perhaps they could be subtly guided through small, strategic interventions at critical points. The implications were enormous. If something as simple as toast falling could be controlled through knowledge of its underlying physics, what other seemingly random processes might be similarly influenced? This question would lead Landsman and Kline down yet another unexpected path, one that would connect their work to developments in fields ranging from weather prediction to control theory and robotics. By 2013, their research had evolved from studying why toast falls butter side down to exploring how complex systems can be nudged toward preferred outcomes through minimal intervention. This approach, later termed chaos steering, would prove valuable in fields from materials science to economics. The simple question about falling toast had opened the door to a new understanding of how order and disorder function across the universe. In 2014, Zachary Landsman received an unexpected email from NASA's Jet Propulsion Laboratory. Engineers working on the Mars rover program had been studying his toast research to solve a problem with solar panel deployment mechanisms. At first I thought it was a joke, Landsman recalled, but they were deadly serious. The principles we'd identified in falling toast, particularly how material memory affects rotational dynamics, had direct applications to how mechanical components behave in the near-zero gravity environment of space. This was just the first of many surprising applications. The chaos steering techniques developed to control toast landings were adapted by financial analysts to develop new risk management strategies for volatile markets. Environmental scientists applied similar principles to river restoration projects, using minimal interventions to guide natural water flow patterns. Perhaps most surprisingly, medical researchers found applications in understanding how proteins fold, a process that, like falling toast, involves complex rotational dynamics influenced by microscopic forces and initial conditions. What we're seeing is a perfect example of how fundamental research, even when it begins with something seemingly trivial, can lead to insights with broad applications, said Dr. Eleanor Hammond, director of the National Science Foundation, in a 2015 address. The physics of falling toast has become a case study in how complex systems operate across different fields. By 2016, the implications had extended to philosophy of science. The toast research challenged traditional reductionist approaches that sought to isolate variables and study them independently. Instead, it demonstrated the value of studying systems holistically, recognizing that emergent properties often arise from the interaction of multiple factors across different scales. We've been taught to break problems down into smaller pieces, Kline explained in her 2016 TED Talk, which has since been viewed over 15 million times. But some phenomena can only be understood by considering how different pieces interact across time and scale. Falling toast taught us that sometimes the most important part of a system is not the components themselves but the relationships between them. This philosophical shift had practical implications for how science was conducted. Research institutions began developing new interdisciplinary frameworks specifically designed to study complex systems where traditional reductionist approaches fell short. In 2017, Landsman and Kline published a follow-up paper connecting their toast research to broader questions about determinism and predictability in physics. They proposed that many systems exist in what they termed practical indeterminacy, technically deterministic according to physical law, but so sensitive to initial conditions and complex interactions that precise prediction remains impossible. This isn't just about toast, they wrote. It's about reconciling our theoretical understanding of a deterministic universe with our practical experience of unpredictability in complex systems. The paper sparked debate among physicists about the nature of causality itself. If systems like falling toast demonstrate how microscopic differences can lead to macroscopic unpredictability, what does this tell us about our ability to fully describe cause and effect in the universe? In 2018, this philosophical question took a practical turn when the team collaborated with computer scientists to explore how their insights might inform artificial intelligence research. Traditional AI often struggled with physical prediction tasks that humans find intuitive. The difficulty in programming a computer to predict how toast will fall highlights something important about human cognition, explained Dr. Raj Patel, an AI researcher who collaborated with Landsman and Kline. Humans don't solve physics problems by calculating equations. We develop intuitive models based on experience that incorporate tacit knowledge about how complex systems behave. This insight led to new approaches in robotics, where systems were designed to develop intuitive physics models through experience rather than explicit programming. The resulting robots demonstrated unprecedented ability to manipulate unpredictable objects, from picking ripe fruit without damaging it to handling delicate materials in manufacturing. By 2019, the research had come full circle back to its origins in everyday experience. A cookware company collaborated with Landsman and Kline to design what they called Murphy-proof dishware, plates and cutting boards with subtle design features that changed how toast slides off edges, dramatically reducing the butter side-down phenomenon. It's not about defying physics, Landsman explained at the product launch. It's about working with physics, understanding how small changes in initial conditions can lead to preferred outcomes. The products became bestsellers, saving countless breakfasts from disaster. But beyond this practical application, they represented something more profound: how scientific understanding empowers us to navigate a complex world. Environmental scientists took particular interest in the research as it related to resilience in natural systems. The discovery that toast developed a memory that influenced future falls paralleled observations about how ecosystems respond to repeated stresses. What Landsman and Kline discovered with toast memory effects has striking parallels to how forests respond to recurring wildfires or how coral reefs adapt to temperature fluctuations, noted Dr. Maria Rodriguez, an ecologist at Stanford University. These systems don't just respond to immediate conditions, they carry imprints of past events that shape their future responses. This connection between toast physics and environmental resilience led to new modalities for studying ecosystem recovery after disturbances. Instead of viewing natural systems as returning to a fixed equilibrium state, scientists began exploring how systems evolve new states shaped by the history of disruptions they've experienced. By 2020, what had begun as an investigation into a breakfast annoyance had blossomed into a rich scientific paradigm with applications across disciplines. The research exemplified how science progresses not just through studying the exotic and extreme, but also by looking deeply at the ordinary and finding the extraordinary within it. In 2021, 26 years after that fateful physics conference where a casual joke sparked his curiosity, Zachary Landsman stood before a packed auditorium delivering the keynote address at the International Conference on Complex Systems. "We began by asking why toast lands butter side down," he said. "We ended by discovering something profound about the nature of complexity itself. The universe is not conspiring against us when our toast falls butter side down. Rather, we're witnessing the beautiful, complex choreography of physical law unfolding in our kitchens." On the screen behind him, high-speed footage showed a piece of toast rotating in slow motion during a fall. The image was strangely beautiful, the golden brown bread turning gracefully, butter glistening under the laboratory lights. What makes this ordinary event extraordinary is not just the physics involved, though that's fascinating enough. It's the fact that in this simple act, we can observe the convergence of multiple scales of reality, from quantum interactions to macroscopic rotations, all unified through the mathematics of chaos and complexity. Landsman paused, looking out at the audience. And perhaps most profoundly, the falling toast teaches us something about knowledge itself. When we truly understand a phenomenon, when we see beyond its surface to the principles that govern it, we transform our relationship with it. What once seemed like bad luck or cosmic malice becomes a window into the beautiful machinery of nature. He clicked to the final slide, showing the equation they had ultimately developed to model the complete physics of falling toast, an elegant mathematical expression that incorporated everything from initial conditions and air resistance to material memory effects. In the end, the most important discovery wasn't the equation that predicts how toast falls. It was the recognition that even in life's small frustrations and mundane disasters, we can find gateways to understanding the fundamental nature of our universe. And in that understanding, we find not just knowledge but a kind of freedom. The auditorium erupted in applause as Landsman concluded with the words that would become his most quoted statement. The toast falls according to its nature and the laws of physics, neither malicious nor merciful, simply true to the magnificent clockwork of reality. Our task is not to lament this truth but to marvel at it, learn from it, and occasionally, when we've understood it well enough, to give the clockwork a gentle nudge in our favor. As the applause continued, Felicity Kline joined him on stage. Together, they had transformed a simple question into a scientific odyssey that spanned decades and disciplines. The journey had taken them from kitchen counters to NASA laboratories, from philosophical debates about determinism to practical applications in robotics and environmental science. And it all began with a piece of falling toast, a humble reminder that the universe reveals its deepest secrets not just in the collapse of quantum waves or the collision of galaxies, but in the ordinary miracles that unfold around us every day, if only we take the time to look, to question, and to wonder. In the dance between order and chaos that governs everything from falling toast to forming stars, we discover not only how the universe works but also our place within it. Observers capable of discerning pattern amid complexity, finding meaning in the seemingly random, and occasionally, with knowledge hard-won, influencing the outcome of the dance itself.